Algebra 2, we are starting chapter 11, which is actually on probability. And before we even get to actually talking about probability, we're actually going to talk about ways to organize outcomes and also how to count things. So take a look at example 1. We have a tree diagram. And the tree diagram is really going to come into play right here. Two things will happen. A coin is flipped. You could either get heads or tails. And a die, or a number cube, as this company is calling it, is rolled. So you can see this first branch right here. You could either get heads or tails on the coin. But from there are 6 sides on a dice. So, perhaps you could then get a 2. So this outcome that we're seeing right here, this branch would indicate that a head showed up for the flip of the coin, and then the number 2 was rolled on the die. And you can see you can have 1, 2, 3, 4, 5, 6, any of those numbers showing up for heads. Likewise, you could have had tails, you'd have the same thing. But once again, wherever we have a little branch here, that's always going to be indicative of the outcome that's listed on the far right. So it says, how many outcomes are there? Well, you can see that there are 6 outcomes with heads, and that there are 6 outcomes with tails. And 6 plus 6, of course, is going to be 12. How many outcomes involve tails and an even number? Guys, the word "and," of course, is implying that you must have tails and the even number together. So you could have a tails and a 2, a tails and a 4, a tails and a 6. It's not enough to just say that a 2 showed up on top, right up here. That's no good. That would be a head and a 2. The word "and" means both have to occur at the same time. So you can see right here we've got 3 items. The answer would be 3. And then, as we wrap this up, it says, how many outcomes involve rolling a 5 or a 6? Now, the word "or" means it's either a 5 or a 6, and it could also be an inclusive "or." Here it's impossible, but you could say either outcome or both. Obviously, you can't roll a 5 and a 6. Later on, we're going to be talking about that. Well, here we could roll a 5. Here we could roll a 6. Here we could roll a 5. Here we could roll a 6. You could say, well, how many outcomes would that be? Clearly, you'd have 4. You can count them up right here. So that's a great way to organize outcomes when you have things occurring, and that's a wonderful thing to keep track of. You can see every possible outcome. We're also going to find a way to count. The fundamental counting principle, or also known as the counting principle, is in this box. If there are m ways to do one thing, n ways to do another, then there are m times n ways to do both. Let's read a problem together. It says, Ryan must choose between a shirt and a pair of pants. He's got 3 shirts. He's got 3 pairs of pants. How many different outfits can he make? Well, he's got to make a choice about a shirt. He has to make a choice about the pair of pants. He's got 3 possible choices for the shirt. He's got 3 possible choices for the pants. All you do is you multiply those 2 together, and you are done. Let's take a look at a more classic question here. For a dinner special at a restaurant, a customer must choose a salad, an entree, a side dish, and a dessert. And here are the items to choose from. Well, we can see that for a salad, you could have Southwest or a Garden. That would be 2 different ways somebody could choose a salad. For an entree, you could have salmon, lamb, grilled chicken, T-bone steak, or roast turkey. Count those up, you could see we have 5 different choices for the entree. For the side dish, you could have French fries, baked potato, pinto beans, rice, or corn. Once again, there are 5 different items that can be chosen. Finally, for dessert, apple pie, chocolate cake, and brownies, well, that would be 3. So how many dinner specials are possible? How many different plates could be formed out of these choices? Well, 2 choices for a salad, 5 for an entree, 5 for a side dish, 3 for a dessert. And guys, you just multiply those all together. So, more or less what we do is we just take 2 times 5 times 5 times 3. And very quickly, we'll just get 150. So as we take a look at this final problem, this last one, it's a little bit more involved. You can see that it says a supermarket wants to send codes for a 25% off a bag of chips to its reward program members. So each coupon code will have 1 digit followed by 4 letters. So we're going to have a digit right here. Now we've got 1, 2, 3, 4. Right here, this would be letters. So this is a code. But this is getting more complicated. We know that there are 26 letters in the alphabet, but D and E, as well as the digits 0, 5, and 8, will not be used. So we've got 26 letters in the alphabet. But the letter D and the letter E are not used. You're losing 2 choices. You're going to be down to 24 possible letters. Likewise, when you have digits, there are 10 digits. You've got the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 that could show up like at a particular space in a phone number. It's one of those numbers. There are 10 of them. But they're saying, look, 0, 5, and 8 are not allowed. You're losing 3 choices. They're being exceptionally kind to you. They're actually telling you how many choices you really now have. And Alex will always do that. So 24 letters, 7 digits. Assume that the letters can be repeated. So you could get the letter A showing up with another A after it and so forth. How many possible choices do we have? Well, let's see. Digits. Well, we've got 7. 24 for each of these. Wow, look at that. Each time. And the fundamental counting principle is saying multiply those choices together. So it's 7 times 24 times 24 times 24 times 24. You'd have 4 24s. By the way, there's a smarter way to do that, isn't there? If you've got 4 24s, how about we raise it up 24 to the 4th power? Regardless, you will have 2,322,432 different codes that can show up. And guys, that's it for our lesson today.